From the brightest galaxies and stars, to the biggest buildings and infrastructure, to that coffee cup you desperately need in the morning, it might not surprise you that matter is everywhere. By exact definition, matter is anything that A, acquires mass, and B, occupies space. But let's ask a different question, like what is the fundamental building blocks of everything in the universe? You might think that's simple. Well, everything is made from chemical compounds and molecules, which are made from even smaller things known as atoms, which are made from even small things known as subatomic particles, which are made of things known as elementary particles, which are said to be fundamental. But if elementary particles are fundamental, what are they made from? Now, let's start simply. As of the works of Max Planck, it was discovered that light could only give different colors in discrete amount of energy. Albert Einstein used Planck's idea of discreteness to light itself, discovering that light was both waves and particles at the same time. Louis de Broglie, a French PhD student, used this idea to matter, concluding that matter also behaved like waves and particles. Uniting these scattered ideas, quantum mechanics was formulated between 1925 and 1926 with important contribution from Werner Heisenberg, Max Born, Erwin Schrödinger, Niels Bohr, Wolfgang Pauli, Richard Feynman, and of course, Paul Dirac. Now, quantum mechanics success showed that the mathematics worked. It was true, very true, and of all the quantum theories, the most successful, most predictive is quantum field theory, or QFT. Now, quantum field theory is a theoretical framework. It's a mathematical description that describes the fundamental workings of reality itself. It was first formulated by Paul Dirac in the late 19th century when he tried to quantize the electromagnetic field. Now, QFT describes all particles as vibrations. And this is the postulate of QFT, that all particles are really just vibrations on their underlying fields. Particles aren't fundamental, fields are. And these fields are water-like substances that have a certain value everywhere in space. A particle is just more amount of that value. For example, the electron is just more amount of electronness on the electron field, which we perceive as the particle electron. You can also observe another one of these fields indirectly, the magnetic field with magnet and iron filling. You've also been observing another field you like, the field of gravity, which turns out to be space and time itself. But how do these fields make particles? Well, as explained with Planck's idea of discreteness, these fields too need a discrete amount of energy to produce a particle, which if you're confused is because energy and matter are the same thing, as explained by Einstein's famous equation E equals mc squared. Energy and mass are equivalent. We can make matter from energy. So for example, if you wanted to create, say, an electron, all you needed to do is deliver exactly 511 kilo electron volts of energy to the electron field, and boom, you got yourself an electron. This number is also the mass of the particle. So mass is really just the amount of energy you need to create it. Now, all these fields are continuous, meaning the fields of a coffee cup and mountain are the same. Everything in the universe is continuous. They're made of the same fields. Now, each field also has an associated particle with it, and each particle has an associated field. There is the same number of fields and particles in our universe, and since at the time there was thought to be 12 particles, there was said to be 12 fields. But after another of Paul Dirac's successes on the Dirac equation, it was found that particles with same mass but different charge could exist, giving way to negative charged particles, making a total of 24 fields and particles in our universe. You should also note that these particle fields are all in the same field. Now, when these fields interact with one another, they acquire properties to the particle. For example, when the electron bends the Higgs field, this interaction gives the particle a property known as mass. When the electron surpasses the electric field, it acquires a property known as electric charge. And all particles get their properties by interaction with these fields. Now, the most successful, most predictive of all of QFT's formulation is quantum electrodynamics, or QED, which was developed by Paul Dirac again after his successes in the second quantization revolution. I mean, what can I say? The man was a genius. But the theory was fully completed by Ichiro Tominaga, Richard Feynman, and Julian Schrödinger, who, boom, got themselves a Nobel Prize. Now, even though QFT is filled with really hard mathematics, we can simplify them using Feynman diagrams. So that's it. That's the basics of QFT. The next time you think about the universe, don't forget to thank the endless curve of these quantum fields that gave way for your very existence. Thanks for watching.